Alright, it's time to get started. So here goes nothing. So during yesterday I was doing a bonus stream where I made some unit tests for the upcoming instructions of the CPU. So hopefully we will have some more fun today. The video is of course on Twitch if you want to see it, but unit test is not so important, right? It was just something that was eating the time of our stream. What we want to see is actual code that is running on the CPU. So the next two operation is branch equal or branch if not equal. Let's find documentation about it and let's get started. So here is the unit test for it. I have these push warnings until our functions are implemented. So this is what the code does. Here we have, this is branch equal, which means it will jump if the zero flag is set. If the zero flag is set, that means that the comparison was a zero, and that's how it knows it is equals. This code loads 3 in the emulator, and it checks if it is equal. Meaning it checks if the zero flag is set. Because the zero flag is 0 by default, it will be unset, meaning it will not jump. So this byte is part of the operation, and the next operation is load again a 5 and transfer it to the X register. And now what we want to check is this is F3, so that means it should have jumped, but apparently I am dumb and I didn't realize the zero flag was not set. So this is meant to be a 5, not a 3. In this other test, we load a 0. Alright, now we load a 0. Because we loaded a 0, checking the 0 flag, it is now set, and it will jump 2 spaces and will transfer that 0 to the register X, and that is what we are checking here. Same test, this is the branch not equal, and it will jump if 0 is not set. We are loading a 3, this means we are not a 0, and the jump will execute, meaning we are going over this, and we will transfer the value to the X register. And because of that, the X register will be a 3, which is the value that we had on load. So this was just inverted. Next, we load a 0 and we check. Jump is 0 flag is clear, because it is set, it will not jump, meaning it will also load a 5 and then transfer it. So this is meant to be a 5. So this is the unit test. We have saved the time of writing it. We should did a quick check if it was correct or not, and of course it was not, because it's difficult to write in assembly and much more written with bytes only. So what we have to do is actually implement the instruction. The good thing is that we can reuse code that we did past string. So let's find our NES CPU. Let's close some scripts and find our NES CPU. So here is where we was working. We implemented ASL, BCC and BCS, and this is where we are now. We are going to implement branch if equal and branch if not equal. We'll duplicate one of these and let's clear some stuff to complete it later. So branch equals the addressing mode is relative, doesn't need any kind of special treatment for addressing, and opcode is FO. Instruction is branch equal, and branch if flag matches. So what we want is the 0 flag is unset. This was a 0, not an O. And that should be all for branch equals famous last word. We scroll down a little, we'll find branch not equal, and the opcode is TO. Opcode name is branch not equal. 2 bytes, 2 cycles, same as branch equals. We are testing the seed flag, and we are going to jump if the 0 flag is set. Wait, is that right? Yes, if this sorry, we jump if the 0 flag is set on branch equal, and we don't jump if it is clear. So let me confirm that. I may have messed up my unit test. So branch equals means the 0 flag is set, right? Okay, yes. It's indeed what is expected. This is confusing. I'm sorry. So branch equals will jump if the 0 flag is true, and branch not equals will jump if the 0 flag is not true. And because we already have had this function implemented, we should be able to test it. So let's uncomment the execution of our functions and see if our test passes. Okay, it seems to have failed. Let's see what is on register X. And register X is a 3, which is what I expected in first place. So let's see what is happening. We are loading a 3. 3 is not 0, so the 0 flag will be clear. So it should not jump and should load a 5. What does that mean? does load not set the 0 flag? See, CPU flags, and the 0 flag is off. What I am doing wrong? FO branch equals branch if flag matches 0 is true, so it is not jumping. Let's test that condition. Let's run it again and see why it's failing. So are we in the function that we are meant to be? This is branch if carry clear. This is not the test. And this is branch if carry set. This is not the test. And now we are in branch equals. So we are in the code that we want to test, and we have read the opcode 240, which is programmer calculator 240 is FO indeed, and we are going to read the next argument, which should be a 2. Yes. And now this is setting the jump value as negative if necessary. Jump at 1, and then what is happening is that this is always jumping. I am not checking if the flag matches or not. So that is the problem. Oh, that was a huge mistake. If flag dot value equals p is set, then all of this should happen. Otherwise, the program counter will not change and it will just advance normally. So let's see what happens now, because I am surprised that this did not fail before. Okay, now it have passed. The previous tests have passed currently, meaning I wrote them badly, I suppose, because it seems they was always jumping, and that did not cause an error until now. Anyway, branch equals now work, and branch not equals as well. So let's commit that. Opening my project. The status. Yeah, we made some changes. So we added the opcode. We fixed our branch function. We uncommented the test and fixed them. Now git commit. This opens the editor. Let's say implement branch equals and branch not equals opcode. Closes. Let's see which one does it close. 13 and 14. Git push origin main, and this one should be sent automatically to done. The next is the bit opcode. So let's see what is the bit opcode about. Where are you? Here. This instruction is used to test if one or more bits are set in a target memory location. The mask pattern in A is ANDed with the value in memory to set or clear the 0 flag. The result is not kept. Bits 7 and 6 of the value from memory are copied into negative and overflow flags. So let's see what is our test case for bit. Same as before, I have a warning for incrementing the execution of the test when the opcode is created. So let's increment that now, and we will see that it fails if we try to execute because the instruction does not exist. And let's break down what does this make. This will load in the accumulator this binary number and will make the test bit with whatever is inside the memory in the location 05, because this is 0 page access, and then ends the execution. Now if we make a bit operation between this byte and this other byte, you will see that the result will be something like this. These both are the same, these are not, and these are the same, and these are the same, and this is not. So the idea is, if these would have matches, the 0 flag is set to true. Sorry, if none of them matches, the 0 flag is set to true because this would be a 0. And the other part is whatever are the 7 and 6 values are sent into the... Wait, it's M? It should be N flag. The negative and overflow flag. I'm so glad I am looking at this before executing. M does not even exist. So the result of this is not 0, so 0 is not set, and the values are transferred in here. And for this one, this is exactly the same bit operation. So this is not what it should be happening, is it? So what should be happening is that nothing matches. So this should not match, and I don't care of these 4. And this should not match, and I don't care of this one. So now 0 is going to be true, negative is going to be false because this is not negative, and override should be true because this is a 1. Okay, we have fixed that now. and this is absolute. This was 0 page and this is absolute, and the only difference is that it takes 2 bytes for the memory address instead of 1. And if this value is the same, that means that we have to fix the same issue in here by copying this value and moving it here. So the execution is load this binary, make a bit comparison using 2 bytes now. This is little endianness, so it goes first the less important byte and then the more important byte, and the result is stored in the register. So we will test the register because we have matching in these instructions. This is not 0, so 0 is set false. And negative and override flags are copied into the register. Now this one, it does not matches at all with the content, so this one is a 0 indeed. So 0 is set to true, but also negative should be false. We have to change that value, and override is set to true. Okay, so we have checked our test case. It's good to have it written beforehand. And let's implement that function. So how is this function called? Let me check once again. This is a bit test. Distraction free mode, and we are going to make our function right below branching. Here comes bit function. Did test again with it test accumulate it test register value. No, bit test register. So we are going to pass a register. And we are going to pass the addressing mode. It's a register, not register. And first of all, we get our address and get our value. We always do. Did I write it wrong? Oh, it was 2 S's. Okay, get our address from the addressing mode and then get the value from the memory. And once we have the value, we are going to make a bitwise AND operation. Value and B register value. Wait, when did I delete that symbol? Okay, and this is of course an integer, and we should now update our flag. So flag 0 is going to be result equals 0. Oops, this is value. and negative flag and override flag. Negative flag is going to be result and one shifted 7. And bigger than 0. So the value here is a boolean, and we can safely convert an integer to boolean. I am just thinking if I should force the instruction. Let's just keep it like this. And this is the negative flag, which is 7, and this is the override flag, which is the 6. Now let me check something. Okay, so the value is copied from this value, not from the result. So little mistake there. Moving out, and this should be the bit function. It should be working. So let's register it. So it was after branch equals and before LDA. We should register bit. Copy this line and let's see. So the opcode is bit. The function name is bit test register, and we are going to bind the accumulator register. And the second argument is the addressing mode. The first of the addressing mode is 0 page. And the second register addressing mode is absolute. Now we have to update the actual opcode. It's 24 and choose C. 24 and choose C. The bytes are 2 and 3, 2 and 3, and the cycles are 3 and 4. 3 and 4. And if I program everything correctly, this should survive our bit test and print these two lines when executing. It did not survive, so let's see what did wrong. This test, this bit comparison, is not a 0. So why does it expect to have a 0? See, register flag 0 is unset. Wait a second. Oh, I see the problem. So the problem is I forgot to write dot value. So let's try again. Okay. We matched the 0 flag, we matched the negative flag, but we didn't match the override flag. CPU flag, override flag is unset. And why did that happen? Let's see what is happening. Okay. Okay. So A and M is from memory. So we should get the values from memory. And the value from memory is this one. So this one negative is true and override is false. So it was correct before. This will also be true and this one will be false. For this one, it's also the same, I guess. True and false. True and false. Oops. What did I change? So I did the right implementation and wrote the wrong test. So that is what happens all of the time for me. And it passed now. Here are our bit absolute and bit 0 page tests passed. So now we have bit instructions executed. It added import, added the opcode, created our function, fixed the test and enabled the test. Git commit, implement bit opcode, closes, issue number 15. Git push origin main. Next instruction, have them coming. BMI and BPL are branch if minus and branch is positive. So they are going to be probably implemented together. I don't know. Maybe I make two separate functions for them. So let's try to get them started, but they are in the same test. So let's see how they work. Both of them are relative. The only byte that they take is the jumping offset. So branch if minus, if the negative flag is set, then add the relative displacement to the program counter. If the zero, and branch positive, if the negative flag is clear, then add the relative displacement to the program counter. So we already have the function for it. We should have to define it. That means that our next instruction is going to be branch minus and branch positive, branch minus, and this will branch if a flag matches the flag is the negative flag, and we don't need any addressing at all. Instead, we want to say if it is set or not. So this is branch if minus, so the negative flag should be set. And for the positive, we are going to branch if the negative flag is unset. Where is my music? Branch minus takes the opcode 30. Takes 2 bytes and 2 cycles. Branch if positive takes the opcode 10. It takes 2 bytes and 2 cycles. So, if I am not crazy, this should be all for the CPU, and we only have to check if our test passes, and of course if it is well written. So this test will load a value to the A register and make the test. Is it positive or negative? In this case, this is not negative, so this should not jump, meaning it should load a 5, and then the instruction will transfer whatever is in the accumulator to the X register. So because this was not negative, this should have not jumped and it should load 5, meaning that this test is wrong. And what is the difference with this other test? It is the same test. Holy. So what we want to do here is load a negative value. So the easiest way is just use binary 4, 5, 6, 7, 8. So this is a negative value, and because this is a negative value, this will jump and will not load the 5 and will transfer this value to the X register. This is more or less the same. This is the command 10 now. It will load a 4 and it is a positive, so it will jump and will not load this 5. So this should be indeed a 4. And for the second case, we should first load a negative. Because this is a negative, it should not jump, and then it should load a 5. Because of that, it should be finding a 5 in this register. Let's try it out. And it passed. Where are you? This is branch plus. I don't find it here. Is this in the scene? Yes, below bit. So it should be in here, but it is not executing because I never uncommented this line. Another shot, and it is still passed. And here we have branch if minus passed, branch if positive passed, awesome. Hit add import, added the instruction, fix it and enable the test, hit commit, implemented branch minus and branch positive, opcode, closes, let's check. Oh, we never created it. (16 and 17). There we go. Let's move on. Next is branch if overflow is clear, branch if overflow is set. So it's more of the same. Branch if overflow clear, branch if overflow set, and this is the same function that we should use it. Let's just copy all of this, and this is branch overflow clear, branch overflow set. And we are going to branch if the flag matches. The flag is overflow. And the first one will branch if clear, and the second will branch if set. Both takes 2 bytes, both takes 2 cycles, and the opcodes are 50 and 70. And assuming the tests are right, it should be all, except we did not enable them. So let's take a look to the test. We're going to enable the test and take a look. So I had some time to think on it. So this one is wrong because I have just figured it out when I was writing byte that the memory that is copied using the bit command is the one used in the memory. So I need for this to load the value in the memory and not in LDA. So let's say CPU memory main write, and in the location 2 I will store this value, meaning we don't even need to do anything with the accumulator. So the bit operation will do stuff, and among that stuff it will transfer the override flag, this flag, to the sorry, I am being dumb. I will keep this, but we'll set a different value. and I will now explain why. So it will check if the override flag is set. Because it is set, it will not jump, because it only jumps if it is clear. It will jump 2 spaces if it is clear. Because it is not, it will not jump. It will load a 5 and then transfer the 5 to the register. And because it did not jump, it loaded the 5, meaning that when transferring, this is the value that will appear on the register. And we loaded this 10 to make that comparison. So now we are going to write a different value to the memory. So 2, 3, 4, 5, 6, 7, 8. And this is the address where we want to compare, and not the value. So this is like this, more or less. Sorry, not use it. Okay, now we are going to make a bit comparison between this value and whatever is on the memory queue, and the override flag will be copied. And now we are going to branch if override is clear. Because it is clear, because it was a 0, it will branch and it will not load this 5. And because of that, when transferring, the X register should be at 10. Now we have to make similar fixes to this one. We have to load the memory, except using no, forget it, I was playing dumb. And we want this other memory for the second test. We want to load at 10 instead of this value. And now we want test from memory, make a bit from memory 2. See, I can copy this. Okay. And now we are making a branch if override is set. Because this is set in this case, it will branch and it will not load the 5 and it will transfer the 10. And in this case, because the override is clear, it will not jump, and because of that it will load the 5 and will then transfer it to the register X. So let's give it a shot. We have uncommented it, so here's code nothing. And it passed. Let's make sure it has been printed, and it has. So the test passed. And that, I think that was the last of the tests that I prepared for today. So from now on we have to write new tests for the upcoming instructions. It's better than having nothing, I guess. Git add, and we registered the new opcode. We fixed it. No, this is yes. We fixed it and enabled the test. Git commit. Implemented branch if overflow is clear and branch if overflow is set. Opcode. Close test. Let me see. In theory, I don't even need to create them, but I think it is more professional if I do it this way. Like if it matters, right? Okay. Git push origin main. And from now on, this is unknown. The next task is creating test for the upcoming instructions, and of course the actual implementation. So clear carry flag is really easy to set the flag to 0. So I think this does not even need a test. So I will just not test them. Maybe we'll test only one. But the implementation is very straightforward. So this is clear carry flag TLC clear carry. Let's do clear decimal. Clear interrupt. Clear overflow. And that is the last one I will make in this one shot. So all of this takes 1 byte, all of this takes 2 cycles. I will name this function set flag, and I will bin the flag and bin the value. So let's create the function. Func set flag p flag is a bit flag. That was the name. Let's check. Yes, it's a bit flag, and p is set is the value that we want. So this is easy, right? So it should p flag dot value equals p is set, and that's all. And this is for the clear instructions of all. Let's copy the list from here. And it also works for all the set variant of the same list. So I also expect to have all of that in one sitting, and that's because it's so easy to make them. So the first one is the carry flag, and all of this is meant to clear, so let's fast forward. So copy, and there are 4 of them. Clear carry. Clear decimal. Damn. It did not work as I expected. Clear interrupt. And clear overflow. Is that all? And I think that is all indeed. So let's check the list. Branch overflow. Clear carry flag is the opcode 18. Clear decimal is D8. Clear interrupt is 58. And clear overflow is B8. Compare X, compare Y, decrease the list. Okay, so none of them matter. So what I want to see is the set functions. So I made a little boo-boo, and that is that these are not meant to be SL, they are meant to be SE. So it's a set function. So find the line, and these are all the clear. Now we are going to make all the sets. Set. And let's see, the set is 38, F8, 78, etc. I will remove this first value. They all take 1 byte, they all take 2 cycles. They are the same flag, and they are setting the flag. So set is 38, set is F8, save 78, and there is no set override apparently. Let's confirm that. Set. No, it does not exist, so we don't need you. Thanks. And now with these instructions, it's going to be easier to make some other tasks. Like we would have not needed the beat command for the previous test, having this one. But yes, we have it now. Who cares? So do we make a test for all of these? Why we have this number of errors? I am not aware of. Ah, I see. So the program was still running and I saved a script that does not compile. So let's make a test. And set clear flag. Yeah. A unique set of tests for the mod. Make a note. Set clear flag. Did I make it? Yes. Singular. We'll assign it and let's create it. The set clear flag. And we are going to transfer this to lowercase, and we are going to put all of the test code in the same function. And let's make a function for set and a function for clear. Just to be more organized. And let's bring the list of opcode from here. So this is the list for clear. Let's put it here. And this is the list for set. Let's put it here. And let's create a function. Instruction free mode. So let's copy the usual header. So the set instruction is the easier one, so we are going to make it first. So this is easy. We should call one time each instruction. And then test all the flags are set. CPU flags, and then we want this. It was. Let's check. C, D, and I. C is true. D is true, and I is true. And what did I do wrong? I am missing a comma. And this one is going to be a little harder, but not that much. So we are testing the same flag to be false, and also the override flag. So the first step is going to be set the flag, the next step is going to be clear the flag. So we have cleared everything after setting everything, except for the override flag. We need to make sure it is set before before trying to clear it. And to do that, we are going to use the bit operand. Let's save a memory location that has the override flag set, and let's use the bit command against the accumulator. Using the address where it is stored, and that will set the override flag, and then these functions will set the rest, and these functions should clear everything. So what I am missing here is printing the result, so I will copy this line, paste it here, copy the functions, name, and see if it all works now. Here goes nothing. Oh, it failed. And it did not fail because I did it wrong. It failed because, again, I forgot to write dot value in the register. Second try, and it seems to have passed. Let's confirm. And yes, here our test, and they all passed. So this was quite fast. Oops, I closed it. So what did we do? Clear carry and set carry. Let's just not create it. Clear decimal and set decimal. Clear interrupt and set interrupt. Clear override. They are all done. We created the unit test and also implemented the instructions all in one sitting. So we registered the opcode, created the function for setting the flag, and added the test to our scene, and we created a new file for the test. So git this head. Let's take a look to the test once more, and I see nothing weird on it. Git commit. Implement and make tests for opcode. And here comes the list. Let's reopen Godot. And let's find the name of the test. Bum, 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 bum. It is the clear instructions. And here are the set instructions. Clear carry, clear decimal, clear interrupt, clear overflow, set carry, set decimal, set, and set interrupt. It pushed origin name. So, next, unit test for compare. Compare is not the easiest of the instructions. So, it is easy. I bet it is easy to implement, but not that easy to test. We are going to see it shortly. Here is CMP. So, this instruction compares the contents of the accumulator with another memory head value and sets the 0 and carry flag as appropriate. So 0, carry, and negative are equals to accumulator minus the memory. Zero and carry. It does not say anything about the negative. Okay. In here says set if 7 of the result is set, so it also updates negative. Okay. Seems quite easy. So let's make the implementation before making the test, so we have a more clear idea of what we need to test. We are making a function called compare register. We are going to pass register A and using different addressing mode, different bytes number, different opcode. All of these are called CMP. So let's go and find and create the function compare register CMP. It takes one register and one addressing mode. Let's try this for a moment. So it will load the memory, it will get the memory address, will get the value from the memory address, will get a result, that will be equals to the register minus the value. Now, this is unsigned math, but Godot's integers are signed. That means that I have to do some math in here, to some changes in here to resolve the issue. So if result is negative, I will have to set the negative flag, taking the chance. I can do it like this, like flag dot negative dot value equals to result less than 0. And if it is negative indeed, I will make the result being the absolute value of itself, and then set the negative bit on it. Result or equal the 7th byte. Okay, awesome. And now I want to update 0 but I can update 0 and negative from this result. Just like that, yes. And ignore this one. And I can also update carry from the result. How does update carry work? Did carry? Aha, so it is not what I expect. So how does carry work in here? Set carry if A is bigger than N, bigger or equal. So that is even easier. I can call set flag flag carry to register value bigger or equal than value. That's good, that's good. Carry set if bigger, 0 is set if equals, negative is set if under. That's how compare works, apparently. And if I am not crazy, with this alone we can also compare X and compare Y register. So we can do it all in one sitting. The problem will be testing it, of course. So copy. Let's go by order. Immediate. 0 page. 0x. Absolute. Absolute X. Indirect X. Indirect Y. opcode D9, D5, D5, CD, CD, song, D9. Oh, else. Oh, how long have you been in here? I didn't see you. Hey, for some reason I can never get this screen to work on my phone, but I am on desktop now. How is it going? Well, I gotta make some dinner, but I am gonna leave a lurk here. Good luck. Thanks a lot, Els. I am a little sorry to not have seen your message before. I hope you have a good dinner. I hope you don't need to call pizza, as always. Or maybe you wish you eat pizza? I don't know. It's a good thing to if you like it. D1. So it's up. Let's go bytes. 2 bytes, 2 cycles, 2 bytes, 3 cycles, 2 bytes, 4 cycles, 3 bytes, 4 cycles, 3 bytes, 4 cycles. Did I miss something? 2, 2, 2, 3, 2, 4, 3, 4, 3, 4. Oh, I am missing absolute Y in here. So this is absolute Y. And this is indirect X. So absolute Y is D9, correct? And it takes 3, 4. Indirect X is C1. It takes 2 bytes and 6 cycles. And indirect Y is D1, takes 2 bytes and 5 cycles. So that's a lot of numbers. Should I continue on register, compare X and compare Y? There are 3 of each, so I think yes. Immediate, 0 and absolute. Register is register X. Compare X. Play my music. They are C0, C4, and C. No, wait, this is compare Y. This is E0, E4, and EC. 2 bytes, 2 cycles, 2 bytes, 3 cycles, 3 bytes, 4 cycles. Next one. Compare Y. And this is C0, C4, and CC. 2 bytes, 2 bytes, 3 bytes, 2 cycles, 2 cycles, 4 cycles. Immediate, 0, absolute. And this is the Y register. So in theory, capitalism works. So we have to find how to test it, right? Is this wrong? Yes, set flag C. Not declared. Right, this is flagged, not flagged. Okay, that's better. So I think it's even better we use it like this. Set flag 0 will be equal result equals to 0, and negative will be register less than value. So this matches exactly what the compare instruction says. Awesome. Testing time. So before testing time, let's commit this, because I think it's enough change to be committed. Implement cmp cmx. Wait, I am forgetting the Oxford comma, and cmy opcode. Cool. And now we have to create tests for it. So we did a task that was not even created. So let's put in done, implement cmp cmx and cmy. It's weird that your phone cannot stream. I am glad that it works in your desktop, because I was concerned about that, to be honest. It's good to know it works, that's what I mean. Did I push this? I guess I didn't, so I can put this here and create an issue for it, and it's number 21. So I can git commit amend and change the description to say it closes 21. Git push origin name. It's gone. So now we have to test them. Only that. But actually should not be that hard to test. Oh, except the addressing mode. Okay, let's go. Let's do this. So let's create a new test. For TMP. TMP goes before or after LDA? Apparently it goes much before. Yes, comes much before LDA. Okay. New node. Unassigned TMP. Let's make all of these lowercase. And let's give a name to these functions. Wow. There we go. This is compare register A. And let's see the order of the addressing mode. Immediate, 0 page, 0 page X, absolute, absolute X, absolute Y, indirect X, indirect Y. Save. And this one should be 0 page X before absolute as well. With that in mind, I should be able to print the list of opcodes from the CPU. Here it is, NES CPU. And we are going to confirm they are correct, of course. We was working on TMP. Paste and make it lowercase. And let's start making sure it works. C9, immediate, C5, 0 page, C5, 0 page X, CD is absolute, CD is absolute X, C9 absolute Y, C1 is indirect X, C1 is indirect Y. Okay, awesome. Now we are going to put same here. Oh, it didn't work. Okay, one by one, I guess. C9, C5, D5, DD, D9, No. I misset CD. And this one should be DD. D9. D1 and CC. And if I have no errors, it means I did not. So it's D1. Okay, D1. Awesome. Okay, now comes the hard part. Let's add this file for now. And let's start making useful tests. Comparison. So, how this works? Immediate is going to compare to the immediately after message. So we are going to load the value 0x3 and we are going to compare it D9 with the next value 0x02. So this one is lower, 0x00. Oh, this value is lower, so it is not 0. The accumulator is lower, so negative is true, and carry is false. And what did I forget here? Oh, okay. Oh, it's double OX here. I will clear the chat box. No need to have all the messages. This will make it harder for people to read the documentation. Now let's try another comparison of equal values. So they are equal, so 0 is true. They are not negative, so negative is false. And they are the same or bigger, so carry is true. And now another more test where the second value is higher than the first value. So 0 is false because they are not equal. Negative, carry flag is set if the accumulator is bigger. So this is false, and this will be the opposite. It will be negative because it's I minus memory is less than 0. So, assuming I made this correctly, this should be already executing and passing. And it asserted. So, accumulator minus memory is positive, so it is indeed not negative. accumulator minus memory is not negative, accumulator minus memory is negative. So, okay, it was a mistake in the test assertion. So now it passed. Let's see the print. TMP immediate passed. So the rest is pretty much more of the same. We are just going to change the addressing mode. So we are going to make this same test addressing in a different way. So now we are going to store in memory this 03 in the 03 address, and we are going to invert the comparison. No, actually, let's use the 01 memory so it is not so obvious. So now we are comparing 2 to 03. 2 minus 3 is negative, not positive, and not 0. 3 minus 3 is 0, is positive, and is not negative. 4 minus 3 is positive, so carry will be true. Is not negative, so negative will be false, and is not 0, so 0 is false. And let's see if 0 page passes now. This failed, it says negative true. So it should be negative if the accumulator is less than the memory, and indeed it is less. So what did happen here? I think I did a mistake in the CPU. So I am glad we are making this test, because I set the flag after flipping the bit. Compare register. So negative is register less than value. And it should be the opposite. What does this say? Negative is the 7-bit of result is set. That means that value register bigger or equal than value. 0 is result is 0, and negative if value is less, the register is less than value. But is that right? Let's check our test. The register is less than the memory value. So what is wrong? Let's make a test here. Okay, let's find the issue, I guess. Where is my music? NES CPU. Okay, let's make a breakpoint, but we have to disable or some tests, I think. So I will comment this one, so we go straight to the 0 page, and let's go. So we got register, which should be register A, right? And addressing mode, which should be 0 page. Wait, is it not 0 page? Oh, it's immediate per. What am I testing? Let's check that. Oh, I see the problem. I never changed the instruction, that's why it failed. So let's see if now passes. I will also enable this test again, and let's see if now passes. And indeed passes. Compare 0 page faces. Awesome! Next one. Compare 0 page X. So we can use the 5 memory address and keep using 1, and have a 4 in the X value for the offset. So we are going to first load 4, and then transfer it to the X register. Was that is 0x0005 correct? Let me confirm that. Yes, tag is 0x0005. So if I am not crazy, this should pass. Oh, I also need to change the instruction, or I would have the same issue as before. So let's see what happens. Yep, it seems to have passed. 0 page X passed. So next is absolute. So we don't need X register, so we are going to copy this test, and the only difference is that the memory address needs to be a value of 2 bytes instead of 1. So we are going to 45, and we are going to access that memory address using little endianness, meaning I have to pass first 05 and then the 40. And of course, also change the instruction to CD. And if I am not crazy, this should pass. Famous last word. Except I did not rename the function name, so I should have twice the 0 page X. The 0 page. So indeed it passed, but printed the wrong message. So next is absolute X. So it's pretty much like 0 page X. So I will copy its content, but I will make the same change as I did for absolute A. So what we need to do here is changing the memory address. Little endianness, so it's 0x05, 0x40, and we also need to change the instruction. So the instruction is dd. Wait a second, because this should be 01, because it will then add the 4 and read 4005. Okay, let's give it a shot. Change the print message and run. And it seems to have passed. Let's find absolute X. Awesome. Seems to have worked. So absolute Y should be pretty similar, except we need to load the Y register. So let's see, transfer to Y is A8 instead of AA. So this will transfer to Y instead, and the rest should be all the same. And something failed, and that is probably because I did not change the instruction. This is D9 now, and it seems to have passed. Absolute Y. Cool. So now comes the hard part. Indirect X and Y. I will have to reread some stuff. So, indirect X. Indexed indirect addressing is normally used in conjunction with table of addresses held on 0 page. The addressing of the table is taken from the instruction and the X register added to it, with the 0 page wrapped around, to give the location of the least significant byte of the target address. So what this means is we are going to take this absolute and tweak it a little, maybe absolute X, and tweak it to have something that matches our instruction. So So this takes a couple of steps, but the instruction is C1. This is the last thing we are going to do, indirect X and indirect Y. So X is 4. So this will load a 0-page memory. If I am not wrong, let's confirm that. Addressing mode, back. Yes, it takes 2 bytes, so it takes only one memory slot. So we are going to put a 1, and it is going to add to 4. So we need a memory stored in 0x5. 1 plus 4 equals 5, and it will read 03. Let's put it on here. And the next one, 06, needs to have the 40. What happened with the 3 I wanted to write here? Am I crazy or this is all? Wow, seems to have passed. Indirect X compare. Okay, so indirect Y makes the sum after. So let's first transfer to Y instead of X. This one is going to read from address 1 and address 2, and it's going to read 40 and 3, and will then add 4, and we'll find the address 4007. Skip music. So if I am not crazy, this is wrong yet, because I need to change the instruction ID. And seems to have passed indirect Y compare register A. Git add import. Yep, all new test. No, I don't want this. Or do I? Yes, I want this. I added the new script to the test. Git commit unit test for CMP. Git push. Wait, why aren't you typing? So CPX and CPY are together. Because they are almost free to do, we are going to make them. Oh, I forgot to say it closes. So I will choose close it from here. So we are making a new test. compare x. Here we go. Ba-bum, ba-bum. You know, compare x. Oh, it's CPX, not CMX. Oh, it's correct in here, right? No, it's not. CPX and CP. Why? That was not cool. Well, but I think I will only need this when and if I make a disassembler. But for now, they are just the name of the opcode. Ron Ronuk 913. Mariano, have a good stream. 100 views for... Yeah. Fuck. F you. How do I ban you? Goodbye. Distraction free. And now we have to rename this to CPX. Rename this CPX. And start completing the test. So we need immediate, we need zero page, and we need absolute. We don't need any of these other. These are the instructions. E0, E4, EC. And the instruction is compare register X. Compare register X. E0, E4, EC. Alright, so let's start copying from CMP. So we want immediate. It is immediate. Let's change the print. Let's change the instruction. And the rest should be okay, I think. Oh, we also need to transfer the value of A to X. So OXAA to transfer the value. And I think this is ready to be tested and seems to have worked. Yes, I also need to fix this TMX and rename it to TPX. Okay. So next is zero page test. We are going to copy zero page from CMP, paste it here, change the print, and change the instruction. E4 and transfer the value from register A to register X and see if it runs, and seems to have run. Compare X zero page passed. Awesome. And last one is compare X absolute. Let's copy absolute and change it as needed. So we want to load the value and transfer it to X, OXAA, and then we are going to compare using the EC command to this absolute memory location. Let's change the name of the print and see if it runs. And seems to have worked. Compare X absolute. So that should be all. We have a new file. Oops. And we have fixed on the name of the instruction and added the test script and the node. Right, so we made a single task for both comparisons, so let's commit them together. What I am going to do is duplicate this file because it's pretty much more of the same, and let's start making changes to it. Instruction free. We want to change the opcode, the name of the instruction, and the register where it is comparing. So copy Y uses C0, C4, and CC for copy Y. Now we have to fix the name of the functions. Let's also fix the print. And we want to make a couple of minor changes to our test. We want to transfer to Y instead of X. So let's replace all the transfer to X for transfer to Y. And we also want to change all the instructions to the ones that we want to execute, which is C0 C4 and CC. Okay, save it, and this will not execute because we also want a node in our scene that uses GdScript to run. So let's see if it runs and passes. Compare y immediate, compare y zero page, compare y absolute, and all of them passes. Cool stuff. See this, we have a new file and changes in the scene. Git commit. Unit test for CPX and CPY. Close it. Pa-pa-pam. 20. Git push main. So let's take a look to what we have done today. Did something fail? Yes, I forgot to write origin. Awesome. So what do we have working? We have ADC and ASL, DCC, all the branching methods work, break work, clear work, compare work, and we have up to the middle of the second half, but also the set statement. So we can say we have almost half of the instructions maybe. So we are ending today. With almost half of the work for the CPU done. Thank you very much for watching, and I hope we are seeing you soon. See you next Wednesday, or maybe before, if we make a bonus stream for making unit tests.